Hello everyone. Today we are going to solve this question which was asked in GATE 2020. Consider a paging system that uses one level page table residing in main memory and a TLB for address translation. Each main memory access takes 100 nanosecond and TLB lookup takes 20 nanosecond. Each page transfers to and fro from the disk takes 5000 nanosecond. Assume that the TLB hit ratio is 95%, page rate is 10%, page fault rate is 10%. Assume that for 20% of the total page faults, a dirty page has to be written back to disk before the required page is read from disk. TLB update time is negligible. The average memory access time in nanosecond, round off to one decimal place is dash. So this is the numerical answer type question. And to solve this question, we need to understand how does memory access takes place whenever there is a page fault. What's the purpose of using a TLB, and how does TLB helps in accessing a page in the memory system. And the reference to this question can be found in this NPTEL lecture 4650, week 10, operating system fundamentals by Professor Santanu Chattopadhyay, IIT Kharagpur. Lecture 46 deals with the translation look aside buffer or TLB part, whereas lecture 50 deals with the page fault part. Whenever, and this falls under the virtual memory part, wherever they are known as the demand paging part. So some useful concepts for solving this question. So the average access time in a system like this will be the TLB hit ratio into TLB time plus the main memory time plus there is a TLB miss, the TLB miss rate into the TLB time again plus uh, the no page fault whenever there is no page fault present in the system, that rate into twice the memory time plus the page fault rate into the page transfer time from disk and again plus the memory time. So what happens is that whenever we are accessing a page in a system, we first have to look at the page table which is present in the memory unit. So that will take consume one memory time, and then from that after we get the page in the page number in the page table, then we will go to that page in a particular page in the which is residing in the main memory. So total it will take twice the amount of main memory time. However, whenever we are using this translation look aside buffer, it keeps the most referred page numbers in it, so that the searching time in the page table can be reduced. So that's the purpose of TLB. So in that case, the time which is consumed twice for searching the page in the main memory, that is one in the page table and another one is the main memory to search the particular page, it is reduced to the TLB time plus the main memory time. The next part is that whenever there is a page fault, whenever the page is not present in the main memory, so what will happen that the OS will bring that particular page from the secondary memory to the main memory. So that will consume some time. So that is referred as the page fault rate whenever when the page is not present in the system. So this will be the, if we all put all the values in that particular formula, then we will get something like this. So there are some extra points in this expansion as well. Like I will go through the steps by steps. Like the first is the 0.95, which is the page fault, oh sorry, the TLB hit time into the TLB time, that is 20 plus 100, that is the main memory access time or the time to search the memory page in the main memory. Next 1 minus 0.95, it's the TLB miss rate into again 20, TLB will be searched every time, so TLB plus zero point 0.9. It means that the page is present in the system whenever there is no page fault in the system. So page fault rate was 0.1 or 10%. So if there is no page fault, then the no page fault rate will be uh, 1 minus 0.2 or 0.1, that is 0.9. into 100 plus 100. 100 will be to search the page number in the page table, plus 100 will be the time required to search the page in the main memory, plus zero point 0.1 if there is any page fault present in the system. Then it was also given in the question that in 20% of the page faults, there are some dirty bits present in the page, and the page needs to be written back into the secondary memory. So in so what will happen is that zero point 0.8 times or 80% times there will be no dirty bits present in the main memory. So what we can do is that we can bring the pages directly from the secondary memory to the main memory. So that will consume 5000 nanoseconds, which was given as in the question. Plus again, to search the page in the main memory will again consume 100 nanoseconds. Plus, whenever there is a dirty bit present in the system, then 5000 nanosecond will be taken to write back all those pages back into the secondary memory, plus 5000 nanoseconds will again be taken to bring the required pages from the secondary memory to the main memory. So the total time consumed whenever there is a dirty bit will be 5000 plus 5000, which is equals to 10,000 nanoseconds. So that's what we have written, 10,000 nanoseconds. Plus again 100 nanoseconds will be consumed to search the page in the main memory. And after we solve this equation, we will get the answer as 154.5 nanoseconds, which is the required answer. Hence, the answer to this question is 154.5 nanoseconds. Thank you.